Day 2 of Chapter 19, some additional information on confidence intervals. Being that this is such an important topic, let's take a minute to reinforce everything that was covered in the previous video. With these types of problems, we've taken a sample and obtained a statistic p-hat. We're using that sample and that statistic to make some kind of estimate about the population parameter p. The standard deviation of the population is given by radical pq over n. However, we don't know what p is. That's why we're estimating it with a confidence interval. So instead, we're using p-hat in its place. For that reason, we don't have a standard deviation. We have a standard error instead. Anytime we're estimating the standard deviation with a sample, we call it a standard error. Same equation, we just have p-hat, q-hat in the place of p and q. We also choose a confidence level at the start of the problem. Usually it's 95%, but it can be anything, 90%, 99%, any number. This image here is showing the normal curve drawn for a 90% confidence interval. 90% is taken out of the middle of the distribution. We go into our calculators, load up the inverse normal function. We add in the left tail, which has 5% of that 10% that's left over. And we do inverse normal for everything to the left of that right line there. So we put 0.95 into the area, and that gives us the critical z-score for that confidence level, 1.645. With all that information, we can create the actual interval. We start with the point estimate, which is the p-hat from our sample. We add and subtract the margin of error, which is our critical value, multiplied by our standard error. Okay, it's in this form, written in parentheses. So as an example, let's say we polled 1,000 high school students across the state. 632 report feeling high levels of stress due to their academic responsibilities. So our p-hat is 632 over 1,000, which is 0.632. Our standard error is radical 0.632 times 0.368, which is 1 minus 0.632, over the sample size of 1,000, we get 0.0153. We create a 95% confidence interval. That has a critical z-score of 1.96. So our point estimate, margin of error is that z-score times the standard error. This is actually creating our interval, and we get this as our interval. When we interpret it, we say we are 95% confident that the true proportion of high school students across the state who would report feeling high levels of stress due to academic responsibilities falls between 60.2% and 66.2%. So now that that refresher is finished, we have our interval, and this interval is telling us the plausible range of values for the population parameter p. It's the true proportion of high school students across the state, all high school students across the state, not just the ones in our sample, who would report feeling high levels of stress from their academics. Samples vary, statistics vary with the samples. If we take a different sample, we would get a different result. Maybe if we did it again, 618 out of the 1,000 people we sampled would say, yes, I feel stressed because of my academic responsibilities. If we created a confidence interval around this value, we would get this interval. Okay, we can notice that this is different than this. If we took a different sample and this time got 641, we get a different interval again. Every sample is going to produce a different interval. There's nothing special about any of these intervals. Okay, so the numbers that we have in our interval up here are not special in any way. They're not more or less special than these numbers down here. Okay, what is special is the fact that if we do this over and over and over again, we expect to be correct a certain proportion of the time. Parameters don't vary. There is some true proportion of students who would feel stressed due to their academic responsibilities. Let's say it's 0.65. So what does that 95% confidence mean? It means that if we were to take a number of different samples and create a number of different intervals, we would expect that 95% of those intervals would contain that actual 65% population proportion of New Jersey students who feel stressed by their academics. An actual definition, we are 95% confident that an interval we create using this method will contain the true population proportion within its lower and upper boundary. If we add context and say it in a slightly different way, it could look like this. If we were to take multiple samples of the same size and create an interval for each sample, we would expect 95% of those intervals to contain the true proportion of high school students across the state who would report feeling high levels of stress due to academic responsibilities. So we've seen that the intervals change with every sample we take. They also change with both the confidence levels and the sample sizes. In specific, as an interval gets wider, we're more confident that we capture the true proportion, which makes sense because there's more proportions in a wider interval than there are in a thinner interval. For example, you're 100% confident that you scored between a 0 and 100 on the last test. You're 99% confident that you scored between a 65 and a 95, 90% confident that you scored between a 75 and an 88, etc. Okay, as you decrease that level of confidence, the margin gets thinner because you're less confident that your actual grade is within those two numbers. Every confidence interval is a balance between that certainty and precision. We want to make sure we balance that out correctly. The most commonly used confidence intervals are created at 90%, 95%, and 99%, but we can use any percentage. Now, ideally, we want our level of confidence to be as high as it possibly can be. We want to say we're 99.99% sure that the true population proportion is within these two numbers. And also, ideally, we want our interval to be as thin as we possibly can get it. So we want to say that it's between 20.2% and 20.3%. Obviously, there's a trade-off between those two things because, as I just explained in the last slide, as the confidence level goes up, the interval gets wider. So one workaround to this is that we can decrease the variability in the sample. And the way we do this is by taking a larger sample size. So looking at this equation for standard deviation, we can see that sample size is on the bottom here. So as the sample size increases, standard deviation decreases. This is the same equation that we looked at for sampling distributions. And just like with sampling distributions, when the standard deviation got smaller, the normal distribution got thinner. And the same thing is going to happen with these confidence intervals. They're going to get thinner because this is really determining our margin of error. Margin of error is just the z-score times the standard deviation, or the standard error. So as this gets thinner, the margin of error gets thinner, the interval gets thinner. Sometimes you'll be asked to find a sample size for an interval with a given margin of error. So we're just going to take this margin of error equation, the z-score times that standard deviation, and we rearrange it. So it's n equals, and we plug in everything. We plug in our z-score, p hat and q hat, and the margin of error it gives us. Whatever we get here, we're always going to round it up to the next highest integer. And if it doesn't tell us what p hat is, we use 0.5 for both of these, p hat and q hat. That's kind of like a worst case scenario. So to close out the chapter 19 notes, let's think some more about the confidence interval we created that showed the proportion of students across the state who would report feeling high levels of stress due to academic responsibilities, created with 95% confidence. Our interval is here, 60.2% to 66.2%. By the way, I hadn't mentioned, if we wanted to find a point estimate from this interval, it's the midpoint of those two numbers. Okay, we add them together, we cut it in half. Once we have that, it would be 0.632. We can find the margin of error just by subtracting either of those two margins from the midpoint. So now 662 minus 0.632 would give us the margin of error. Number one, if we wanted to be 98% confident instead of 95% confident, would our interval need to be wider or narrower? It's going to be wider. We're more confident. We need a larger range if we're going to be more confident. Our margin of error was about 3%. If we wanted to reduce it to 2%, would our level of confidence be higher or lower? Okay, so if the margin of error is 2%, it's now gotten thinner. That means that we have a lower level of confidence because now we're less certain that we're actually catching the true population proportion in an interval that's thinner than it originally was. What's another way that we could reduce the margin of error, and what's a drawback of that option? We could take a larger sample. It's more expensive. And lastly, how many people would we have to poll if we wanted to cut the margin of error in half to 1.5%? So we're going to use that sample size equation. We're going to plug in everything we know. So the z-score for a 95% confidence interval is 1.96. The p-hat is 0.632. Here's the q-hat. Margin of error is 1.5%, and we switch it to a decimal, 0.015. Okay, we let our calculator do the work, and we get 3,970.95. This always gets rounded up, so even if this was 0.05, even though it's closer to go down to 70 instead of 71, we would still go up. All right, so regardless of what the decimal is here, we always round this up. Our answer is 3971.